Good. This so next is cancer, reactive species in cancer. We have done quite a bit of work on that, and a lot of work is available on reactive species in cancer in the literature. Okay, I think I have assigned 3 or 4 papers. One is a review paper; it's good to read, not ours. And then 3 of our papers, no, 2 of our papers. One is optional. Steffi's and Uma's. So 2 papers plus a review paper. Okay. Tomorrow is a holiday for I think Good Friday. Okay. So when we meet on Monday, we will start out with an incentive and then discuss that particular part. And then there's one more aspect which I'll assign on Monday, and then we'll meet on Thursday. We'll do something else on Thursday. I'll give you off on Friday, and then the other, I think there are again 2 holidays that week also, but Monday is not a holiday. So Monday we can be, Monday will be 1st, 1 plus 7 is 8th. 8th March is not a holiday. 9th and 11th are holiday, so Thursday is not a. So that way the last class I can finish up and then you can go on to your presentation. See, it's all well set. If something disrupts, we'll have to change it, something, we'll see. That will play it by the ear when it comes. Okay, any questions, comments? Anything else before we start? No. Okay, then let me close this. This is okay, that's fine. So I can close this. This I can close, I think. Yeah. Good. Excuse me. Okay, this is reactive species in nano-bio-systems. This pretty much started, there was a collaborative effort with the IIT. They were looking at nano materials and they wanted our input on reactive species, and that's how this this topic came into being in our lab. The first one to work on that was Archana. She contributed quite a bit on various different aspects. This was a thesis related aspect. It so happened that she was in our lab for almost 10 years in various capacities. She came in as a project student, summer project student, internship, whatever is called internship nowadays. And then she came back. She did her bachelor's from Sastra, so she came back for her BTech project along with her friend, and then she became a project staff, largest project on algal biofuel. So she became a project staff, and then she went out, did a master's, and then she came back for a PhD. So the master's project she did in our lab. So pretty much she was with us for 10 years, very productive in terms of papers. And it so happens that this particular idea was completely hers. She came and talked to me about why don't we do this. It made sense. At that point in time I had the freedom to let people work on their own topics. I was not constrained by funding and so on and so forth. If I get constrained by funding, I'll have to choose an angle that fits the funding because I need to present results. And so that I was free. So at that point in time, Steffi chose her own thing, Archana chose her own thing, Prerna chose her own thing. After that, it has been kind of a mixed bag. And they chose it probably a year into their program, refined. Finally, what they did turned out well. All turned out well. I'm very happy with that. It shows a good level of independence, maturity very early in their programs, so that was good. So from this review paper, we looked at the effect of size of nanoparticles on reactive species, on cellular effects: size, shape, surface chemistry, aggregation, agglomeration, release of silver ions from the surface, and then these are all chemical factors, physicochemical factors. Biological factors impacting silver nanoparticle activity in vitro is the cell type and the biocorona formation. You all know what a biocorona formation is, I suppose. It is there's a certain protein which is expressed, and that protein interacts and forms some sort of a trailing cone behind these cells, okay, and that is called the biocorona. It shows the interaction with protein and things like that. A lot of work is done on that. So the story that I'm going to tell you is Archana's story. She wanted to work on emerging pollutants of concern, or contaminants of emerging concern, as they are called. The CECs are nothing but chemicals that have been used for a long time, but their release into environment is only recently detected, or chemicals recently known for their adverse effects, essentially anything that whose adverse effects came to be known rather recently, and therefore there are no set standards as yet, okay, or newly synthesized chemicals and so on. A number of products can be CECs: industrial products, pesticides, pharmaceuticals, personal care products, nanomaterials, metals, flame retardants, biological sources. And the silver nanoparticles were in this category when she started her work. I think they still are. So the definition is any synthetic or naturally occurring chemical or any microorganism that is not commonly monitored in the environment, but has the potential to enter the environment and cause known or suspected adverse ecological and or human health effects. Okay. So this is according to the United States Geological Survey. This is one of the definitions which is normally followed. Okay. That is what a contaminant of emerging concern is. They essentially do not have federal regulatory standards, or the standards are evolving at the time of work. They could be present in drinking water. All these pharmaceuticals, nanomaterials, flame retardants, pesticides, detergents, preservatives, all are CECs which could be present in drinking water, because there are no standards for them and they were not monitored. Engineered nanoparticles which are used heavily or which have been made for a certain purpose are engineered nanoparticles. Without spending too much time, you all know about this. Therefore, the one which was heavily used, this is 2015 data, and even now there is not much of a change, is titanium dioxide. Titanium dioxide nanoparticles are heavily used because they are UV absorbent, they have UV absorbent characteristics. Therefore, cosmetics like sunscreen, lotions, UV resistant coatings and things like that have titanium dioxide. They are photocatalytic, and therefore anti-fouling paints, antimicrobial coatings and self-cleaning coatings have TiO2. And for this is the oldest application. The paints need opacity for their shine and their desirable characteristics. Titanium dioxide has been used for that purpose for a very long time, many decades. So paints for hiding and for the brightness of the paint, TiO2 is used. So I think the numbers were given here, tons per year, even in 2015 was 60,000 tons per year, 60,000 plus tons per year. So huge amounts were produced. And these are recalcitrant materials. So all that sits on your lotion and things like that effectively will get washed off. Nothing will happen to them. They will ultimately end up in the wastewater treatment facility, and that was the problem. So this is, that's what is given here. The mode of entry and fate, these are technically you say them this way: mode of entry, mode of fate and so on. So domestic applications, including on your skin, the TiO2 gets released, they get into the wastewater treatment plant, and then they are treated, the treated effluent is let out. The standards are quite strict, notional standards are quite strict. You see two different standards here. 10 to 100 microgram per liter is one published work in 2009, 25 microgram per liter in 2011 published work. There are variabilities and so on and so forth. These are not, I don't think they are well established standards, but proposed standards and so on and so forth. Okay. So there are standards. Despite that, they end up in river, lakes and oceans. Irrigation becomes a problem, environment becomes a problem. Widespread exposure, persistence, bioaccumulation, all these are big terms in this context. All this happens, and of course there are toxic effects in all the waters that humans use. So this is what Archana suggested, a sustainable approach for handling nanoparticles, titanium dioxide nanoparticles. So instead of it going from the wastewater and wastewater treatment plant directly to the environment as an effluent, she said we will take this out with the TiO2, we will use this TiO2 and or rather we will accumulate the TiO2 in some microorganism, bacteria, because they are easy to grow. Essentially set up a column of bacteria and you pass it through that, you can get actually clean water till a breakthrough happens. Okay. So that was our idea, and not just that, TiO2 can induce oxidative stress. So choose one such bacteria by which the oxidative stress can be used to improve the productivity of that bacterium. So that way both things get or rather one stone, two birds with one stone kind of a thing. So you end up bioaccumulating TiO2, so that way the volume of the waste becomes much less, and there could be ways by which you could recover TiO2 by burning and so on and so forth. Not highly recommended, but yeah, you could, because they are recalcitrant. And if the organism produces something of interest to us, then because of the induced oxidative stress it produces more, that way it is better. So that's, it induces ROS increases, in this case bio-oil formation. So titania remediation enhanced microbial performance, in this particular case bio-oil from Rhodococcus species, because that is a bacterium. Earlier our earlier work in the lab was looking at microalgae for bio-oil, because that was a trend, and then we jumped into that trend, and then we realized that that is not going to work out, and therefore we started looking at bacteria. Much easier to grow. There is an entire paper on how bacterial source is much better than algal source in terms of numbers and so on. I do not know whether I assigned it to you, but if you look at my web page, Archana's paper, it will tell you justification for using bacteria over microalgae for this purpose, for bio-oil purpose. And then she did the experiments. I am not going to go through the experiments. We have all looked at the paper quite well, and therefore she did 4 different experiments, basically just plain TiO2 with UV throughout, with UV and TiO2 throughout. The UV was throughout, and then UV only from the mid log phase and so on and so forth. There were differences in the amount of oil that was accumulated in the organisms. Of course, the TiO2 was it depends on the way you operate the column. You could actually completely eliminate the TiO2 from the stream. That is not a problem. So that was the data. Here some data on oxidative stress under the various conditions, and again at that point in time we were looking at the lack of, this is the relationship between the oil fame and the specific interstellar hydroxyl radical levels. There seems to be a correlation. As you increase this, the other one increases. The other way around would have been nicer. That's okay. So that is what this is. Okay. So yeah, this is the paper that I was mentioning, investigating the potential use of an oleaginous bacterium, Rhodococcus opacus, PD630, for nanotitania remediation. This was an idea before its time. I was very excited about it, sent it to BNB. BNB didn't want to take a look at it. Biotech Progress didn't want to take a look at it. All desk rejects. We were clearly ahead of time at that point in time. We published it somewhere. These were happening at that time because we were working on entirely new things. And that's what, after 10 years of the work being done, of no correlation between, no, not 10 years. 10 years of the work was published, okay. The work was done 15 years ago. When Sonal gave her seminar this time, she just mentioned one of those from her work related to the lack of relationship between the two, the antioxidant and the reactive species, right? As a part of her work. That was not her work at all. The contribution had happened. The paper was published. The paper was published a little later because we had trouble publishing that. I had sent it to Nature, Science, everything. Everywhere there was a reject. And finally, I had to piggy it back on Uma's work and send it and got it published somewhere. It was published in 2019 or, yeah, 2019. So about 15 years after the work was done, there was a huge interest in our audience saying, how can there be no relationship and so on and so forth. So that's what happens when you do things before your time. I don't care, but that's what happened. I'm sure that's what happened in this case also. We were very sure that this was something substantial, but the scientific community didn't see it that way, so it was published somewhere. Where was it published? Environmental Science and Pollution Research, doesn't matter. So, and this was a surprise. This is the Biotechnology, Bioengineering, the topmost journal in the field. So, Archana had looked at a genome scale metabolic model, hot at that time, 2018 is it? 2020 published, so 2018, 2019 the work was done. Very hot at that time. So, we said it's hot, so let me see. Okay. Straight acceptance, not much of comments even. So, the hotness matters a lot. Of course, the work has to be decent, it has to be sound and all that. Hotness matters a lot in all these big journals. So, I mean, good piece of work, there is no doubt about it. She figured out the mechanism by which this happens through genome scale metabolic modeling. She used, or she took an existing genome scale metabolic model, made it suitable for Rhodococcus opacus, and then did her analysis. Building a model takes a long time, years. So, she did this. And then building a complete model. Nowadays, you can do a context specific model much more quickly, but then context specific models were kind of rare, I think. Not many people are doing it. How many of you, by the way, have done any systems biology? 1, 2, 3. You are doing the course now, isn't it? Good. So, 3. Pardon? Context specific modeling. Yeah. Now that's the way you can get close to your system. Of course, that model is applicable only for that system. You build it from a bigger model and all that using omics data, transcriptomics typically, but very useful. That way 3 years of work gets done, and 3 years of building a model, some earlier times it used to take many years, gets compressed in about a few months. It's still a few months of verifying and so on and so forth. Good, because others haven't done any systems biology, is it? I know Raghav works on that, so he knows, but okay, because the last part I will have to figure out how to be effective, which means I will have to give you some background to that. I'll do that. The 3 of you will find it a little repetitive, that doesn't matter. The ones who are doing systems biology or who have done systems biology will find one of the papers a repeat, but it's good to revise that paper. I'll give you only a 4-page paper on systems biology, and also give you our paper. That's for after cancer. Okay, I think more here. Yeah, this was the paper that I was talking about in terms of how the bacterial system is better, sustainable diesel feedstock, a comparison of oleaginous bacterial and microalgal model systems. So, here she actually shows very systematically through huge analysis of the literature information and our own experiments that the bacterial system is better. So she could get combined titania removal and increased via oil production through this strategy. And her PhD turned out very well. She won the best thesis award and so on and so forth. That's entirely based on papers. She had 10 papers to show anyway for many years, and she used to contribute to others also. So that way it was. She had a knack in that. And that needs a certain orientation. So she had that. Okay. Any questions, comments? Two pathways. Yeah. Those were the ones that came up as a part of the genome scale metabolic model. That was a contribution of that work. So she had used a genome scale metabolic model to identify the mechanism. She first chose one that was obvious from that. Hold on. No. She had used the literature to hypothesize mechanisms. She chose the one which seemed obvious, and analysis with the genome scale metabolic model showed that it was not. And therefore, she looked at the other thing, and with that worked out, which was less obvious. Less obvious is it was not too popular in the literature in that small circle. That's the way it works. And that kind of, for us, the ideas came. We wanted to do something, and therefore, can we do this? And it went forward. It so happened nobody else had done that. Nobody else had used genome scale metabolic models to do this, and that's why BNB was interested. We never realized it. We kind of knew it. We said we didn't think it was great, but straight acceptance in BNB was straight acceptance. There were some comments and all that, but very easily handled. So that was a surprise. I said, let us send it here. If it doesn't go, then we'll. I was all prepared for a desk reject, and I was going to send it to Biotech Progress at least. At that point in time, many were going through this cycle, so I used to sit back. Let us see what happens. That's it.
So there could have been other enzymes which were inactivated by this, right? The OS causes.
Other pathways based on a study of the system, nothing seemed obvious, because even the second one she had to struggle quite a bit to come up with something. She said, oh, this may be, and therefore let us test this out.
Because you're using gen to validate if that is not to identify what.
Not to identify, no. Yeah.
Can that be done with respect to oxidative stress?
Without intervention, I don't see it happening at the current state of things, because that calls for a certain automated decision making process of a reasonably non understood procedure, right. That I don't think models can do. You cannot automate it. You can use it. You can use it to provide certain inputs, and then you make the decision. Yeah, that can happen.
Even of the two pathways that we looked at, the assay was done for only one, the second method.
Because the first one didn't work out at all. Didn't work out at all. She was going to show it experimentally. When there was no possibility there, when the fluxes didn't work out at all, there was no point in digging that further. By the way, this Swagatika was the person who is the expert in genome scale metabolic model. So I think I may have told you the story. Swagatika joined as a Inspire fellow, Inspire teaching faculty, probably in 2016 or something like that. That's a 5-year term. Okay. And she was working with Raghu in chemical engineering, and Nirav was a part of it, and so on and so forth. We kind of came together and started discussing. So it kind of organically came together. Hey, why don't we look at this? Why don't we look at this? That kind of a thing. So at that point in time, we used to have meetings with all our students at a fixed time. Raghu was busy. No, he was not the dean at that time, but he was busy. All of us were busy, so we had 1 hour in a week when we used to meet, and people used to give presentations, things like that, and we used to discuss. So one of the inputs when the thinking went this way for Archana's work was, or one of the considerations was, Swagatika is there, therefore she could provide as much input as possible. She knew the possibilities with systems biology. That was a PhD area, and so on and so forth. Enough experience. She had published Nature Biotech and things like that. So that's how I got into it. That's why I had the confidence to get into it. I wouldn't have gotten into it on my own, because I look at it a little differently, and even the sampling was not there at that time, and so on. So with the sampling, I'm a little better. But that's the approach, because the knowledge is not complete. So at least we get some idea of a holistic picture rather than individual picture. Individual picture is complete, yes, but the moment you bring in the question as to why this and why not that, you don't have an answer with that approach. It's rigorous, yes, and that's what I like about it, but it cannot do any systemic or network kind of a thing. Very simple question. You have studied this, yes, fine. How are you sure that this is even important? I have no answer. And that thought rightly became prominent whenever papers went for reviews and so on. That's the reason we started looking at this. So Swagatika contributed significantly to Archana. She contributed to, she was the co-guide for Prerna's thesis, and so on and so forth. And that was the reason why we got into developing a reactive oxygen species module. It's a big thing. Yes, please.
I have a question regarding the papers that you wrote about, oil production using using oxidative stress.
3 papers. Which 3 papers?
These 2 papers.
These papers, okay.
So, like, you induce oxidative stress to produce triacylglycerol, but won't this oxidative stress induced by reactive oxygen species affect triacylglycerol as well?
Yes, certainly. So what you get is a net thing. Yeah, that's a good question. Let us start with xanthan gum, our first thing to begin with. Xanthan gum is secreted by the plant to protect itself against Xanthomonas campestris. It's secreted by Xanthomonas campestris to protect it against the oxidants that the plant produces to attack the pathogen, right? So it's kind of an antioxidant, or it's a reactive species neutralizing agent. It will get chewed up, right? So what you are seeing is the net effect of the rate of this being produced and the rate of degradation. That's what you see, and that has a good increase.
And are there any mechanisms to reduce the effect of ROS on the product that you might have?
The thing that I can think of is use something that will react much faster with the with the more reactive of the species. That could be one. That's a double-edged sword. It can affect your product of interest, but the effect could be less and so on. There could be ways, but we haven't really looked at that. What we right through in all the studies, what we are looking at is the net result of production and degradation due to reactive species, right, in any system.
And I don't think such an intervention is necessary because it affects your product.
No, without, in other words, you are producing a lot more. When we talked about a 70% increase in xanthan gum, the total increase would have probably been more than twofold, and then something got degraded, and the net was 70%.
So like if you are further studying this process, you can also look at, you know,
Yeah, that could be an angle. If you find a strategy by which you could reduce the effect of reactive species in the product alone, yes, but it's an interconnected thing. You need reactive species for normal life. We are talking of excess rates of excess levels of accumulated reactive species that you are targeting. If you can target that effectively, yeah, definitely, I agree. That's a good strategy, if you can find a method. Any other questions, comments?
Because you had the wastewater aggregator, you were looking at the pollutant first and then looking at the application in terms of bio oil.
I'm sorry, looking at the pollutant first and
First you had this pollutant in mind and then you looked at how to utilize or exploit it and then you had come up with a bio oil.
oh, you should ask Archana that, because I was presented the entire thing as a strategy.
Okay.
It was not mine.
Okay, why I mean that is we're looking at bio oil. If we had just focused on bio oil production, there were other inducers of oxidative stress which are better than that, and everything would have been different. Like
Certainly.
mechanism.
Certainly, and we have rather with microalgae we have done a significant amount of work, as you saw in the last set of papers that you read. We had used UV, we had used chemical induction and so on and so forth. No, UV, light, so all the other stresses we had used in that particular study. It so happened, okay, when I start looking at it from this point, it fits into all other stresses. That's the way it is. So how she came up with the idea, for me it was a package. It sounded fine, it was quite early in her thesis. I said, go ahead, let us see where it goes. Okay. When I do this, I am taking a risk. It's my responsibility to make sure if something goes wrong, then I bring it back. I had the confidence to do that. I knew enough angles to look at it. That's the reason why I said you go ahead. That's the reason why I asked Susmita not to go ahead, because she will do the work, it will not be publishable. I thought it will not be publishable at that point in time. It was not. When we went to publish it, there were questions and we had to tone it down. That's why the paper will say program said, I mean, there will be a like term, program like cell death or something like that we had to use, and not use we could not use apoptosis directly, because at that point in time it was set aside only for mammalian cells. So all these were there, which I knew. That's the reason I asked her not to do it, but she wanted to do it. It turned out to be, and got published. Her aim was to publish it in the science related journals. That was her objective. She tried it for sporulation as well as for the programmed cell death paper, but both went to BNB finally, because the other things would not, one would not accept shear. The science journals did not see shear as a means, they couldn't understand it essentially. So they had a major problem with shear in both the cases, and in the second paper they had a problem with sporulation. They were fine, they were comfortable with sporulation, but they had a problem with program cell death. We called it apoptosis at that time, and then we had to change it to, and we had to call it CL3P like protein or something like that, and so on. So we had to change terminologies. Yeah, that's a part of any community. So. Any other questions, comments? Good. 47, 3 more minutes only, that doesn't matter. That says 45, but the correct time is 47. We started a little early too, started a minute early, so not too bad. Okay, we can close. Okay, people, on tomorrow is a holiday, of course. Monday, please read the cancer papers and come. We'll have a 10-minute incentive to begin with, or whatever minute incentive. And then we'll discuss cancer. We'll have a lot to discuss on cancer. And then Thursday there will be a class. Friday most likely there's no class. I'll decide about that on Thursday. And then the Monday after that we'll have an incentive on the genome scale metabolic model. That will be the last part of it.